In my previous video, I discussed implementing a floating bar mechanisms to enhance the tool changer's efficiency. In this episode of the tool changer project, I will provide additional information regarding the reduction unit I encountered while trying to achieve better outcomes with the floating bar in use. Hi, welcome to Slow Engineering. I'm David. The floating bar leaves multiple tool heads and docks moving up and down to cooperate with the printer's XY gantry. Of the two options discussed in the previous videos, I prefer having the stepper motors outside the printer enclosure. Placing the stepper beside the heated bed doesn't make sense. This decision makes the entire mechanisms on the door frame instead of the printer frame. To move the bar, I need to assess the performance of the steppers. I weigh the tool head and estimate the dock and bar to get the total weight for the floating bar. The tool head weighs 220 grams, the dock weighs about 20 grams, and the bar weighs around 240 grams. Additionally, I calculate the weight of the maximum number of the tool heads and accessories, which comes out to approximately 1.5 kilograms including the bar. I used a 2020 profile for the bar weight calculation, which is heavier than the DIN rail and provides a safer estimation. But the further design will consider using DIN rail as a lighter alternative. The 510mm bar length requires a torque of approximately 187.5 Newton-centimeters for each stepper. However, the holding torque of the NEMA 17 steppers used in the Voron printer is only 59 Newton-centimeters, which is insufficient to lift the bar. To stop this problem, the Voron printer used a reduction with the Z-axis to lift the gantry. This involves using 82s and 16-tooth timing pulleys to achieve a 5:1 ratio reduction to increase the torque. With a reduction ratio 5:1, the stepper will have approximately 5 times the output torque, around 295 Newton-centimeters, much larger than the needed torque of 187.5 Newton-centimeters. Of course, in this state, the torque efficiency is not included. That is why the torque needs more to overcome some efficiency loss. I initially attempted to design a gearbox with a 5:1 reduction inside the door. The gearbox needs to be compact enough to fit within the limited 20mm length of the profile provided. While looking for compact solutions, the first suitable option I found was the planetary gearbox. Planetary gearbox consists of sun gear, a ring gear, and several planet gears. I tried to build one with a 5:1 reduction. Yes, it is a compact solution. With a 12-tooth sun gears as input, 3 18-tooth planet gears, and a 48-tooth ring gear. The carrier of the planet gears will have the 5:1 ratio if the ring gear is fixed. However, when I tried to print the gears, I knew I encountered the common issues of the gears, the backlash. The gears need to have backlashes to make the gears rotate, and even worse, the 3D printing also needs some tolerance to have proper printing clearance. These drive the result, which is not an ideal solution that involves position control. After researching a new solutions, I found runway gearing a good option as it offers precise positioning and low backlash. However, it seems to have to move the gearing outside, leaving only a pulley inside to drive the motion. I then designed a compact 5:1 runway gearbox consisting of an oval-shaped wave generator that rotates inside a flex spine gear, squeezing the flex spine gear teeth to contact the outer circular gear teeth on two sides. The flex spine gears has 10 teeth, while the circular gears has 12 teeth, resulting in a 5:1 reduction. I use EVA filament to make the flex spine gear, which provides more temperature resistance than TPU material. These flex spine gears needs the flexibility to deform to contact the circular gear, and it also needs to be stiff enough to have the rigid teeth and a solid bottom. It will need some time to find a suitable combination. I also changed the tooth shape. The tooth shapes differ from the standard gear tools as I made it sinusoidal to perform smooth engagements and disengagement. I reinforced the bottom of the flex spine gear to transmit motions to the output shaft. The solid part has two set screws to fix with the output shaft, which passes through the door panels with a timing pulley inside. As I didn't find enough space for the bearings to sustain the output shaft, I placed one bearing at the end of the flex spine gear and the other beside the timing pulley. The entire gearbox housing is fixed with the stepper, which makes the total length outside the printer unexpected. What do you think of this solution? After realizing that the Stramway gearbox was longer than expected, I decided to design a pulley reduction system similar to the Voron to Z-axis as another option. I kept the 22 pulley inside the printer while the rest were outside. This combination resulted in a shorter Y direction, but a longer X direction. The gearbox can be fixed directly onto the door frame using only 3 mounting holes. But I decided to make 4 holes since the orientations can change to have the stepper on top. Which solutions do you prefer? A compact Stramway gearbox that provides a clear outline but is longer in one direction, or the same concept gearbox as the printer? Leave a comment to share your thoughts. Or maybe you have a better solutions to balance the dimensions and positioning accuracy. Personally, I wanted to try the Stramway gearing and see how good it would be. If you like this imaginations and building project, you may also like my other building series. As always, moving forward.